In Lesson 5, we're going to talk about the stresses in beams. Chapter 14. So, when beams are in equilibrium, external forces are balanced by internal stresses. We learned that in previous lessons. Beams in bending are subject to induced tensile and compressive stresses, and also shear stresses. Beams will also undergo some elastic deformation under load. And when we consider the beam of this figure right here, we notice that there's a certain amount of bending going on here. Here's our shear and bending moment diagrams. We have a shear load here, we have a shear load here, and then we have a maximum moment here. And that's where our bending stresses are going to be. So when we look at this beam and we consider its deformation, okay, we have these two vertical planes here. Now this beam is subject to bending, okay, and this is kind of exaggerated here, but as you can see, what happens is you have the neutral axis, J to F is the neutral axis, and then from A to B, your line is actually shorter than from C to D. So what we're getting at in pure bending like this is that we have both tensile and compressive stresses due to bending. In the upper segment of this beam, you're going to be subject to a lot of compressive stresses, and in the lower, you're going to be subject to tensile stresses. So if we were to look at the distribution of stress and strain in a beam due to bending, this is what it would look like. So we have any arbitrary section of our beam, we have a shear load, and we have some bending going on. So this would be our strain diagram. So we have our maximum shortening here at the top, and they have maximum elongation right at the bottom outer fibers of the beam. And then we have compressive stresses here and tensile stresses below the neutral axis. So the maximum stresses are going to occur at the outer fibers, and then zero bending stresses are going to occur along the neutral axis. The upper fibers are going to be in compression, and then the lower fibers are going to be in tension. And then we're going to derive the so-called flexor formula. I can let you do that in your textbook. But here is the formula. It's equation 4.1. So what this is M is the bending moment. Okay, so bending moments are causing the tensile and compressive stresses in the beam. We're going to use FB max. I know I used to use sigma here, but let's use this. FB max, that is the bending stress. And the maximum means that it's at its outer fiber, because in this equation, C here is the distance from the neutral axis to the outer fiber. So this equation, 14.1, is going to net us the maximum bending stress. We can rewrite this expression and solve for stress, and what we have here is, this is the generalized flexural formula, 14.2. It says the maximum bending stress equals the moment times C, which is the distance from the neutral axis to the outer fiber, divided by I, which is the moment of inertia. Now, that last formula was for the maximum at the outer fiber. But if we could write it generally, we can say the flexural formula at any distance y from the neutral axis is FB, which is our bending stress, equals my, which is the distance from the neutral axis, divided by I. In some cases, what we're going to have is an allowable moment, okay, in which case we're giving an allowable bending stress. And when we're giving an allowable bending stress, we're going to give it the character capital FB as allowable. And then MR is going to be the allowable moment or moment strength. Now, in some cases, it's nice to put the flexural formula in terms of the section modulus. Remember, section modulus is C over I. Okay. So flexural formula in terms of section modulus, this is good for design problems. That is the stress equals M divided by S, which is the section modulus. And then the allowable moment for that equation would be MR equals FB times S. And then for design problems, our required section modulus equals the moment divided by the bending stress. That is the maximum allowable bending stress. Okay, let's put a few caveats out here about the flexural formula. First of all, the beam must be straight before loading. The beam must be homogeneous, obey Hooke's law, and have equal modulus of elasticity in both tension and compression. Again, very important. The loads in reaction must lie in a vertical plane of symmetry perpendicular to the longitudinal axis of the beam. That is your parallel force system. The beam must be of uniform cross-section. The maximum bending stress must not exceed the proportional limit. Again, very important. 6, the beam must have adequate lateral buckling resistance. Number 7, all component parts of the beam must have adequate localized buckling resistance. Number 8, the beam must be relatively long in proportion to its depth. Number 9, the cross-section must not be disproportionately wide. And number 10, the dimensional changes must not be appreciably affected by shear strains that are also present. Okay, if you have all 10 of these conditions, then the flexural formula is valid. Okay, so in the next section, in the next movie, I'm going to talk about shear stresses in beams.